Hello everyone, now we'll be moving on to a new topic, geometry and trigonometry. The first part that we'll be covering is geometric trigonometry, which is studying about areas, lengths, anything about triangles. So first, let's discuss how to find the arc length, area of sector, and area of the segment. All of these over here are somewhat related to the circle. First of all, how do I find the arc length? Let's say I want to find the arc length AB, or actually to be more specific, this is the minor arc length AB, would just be r times theta, where r is the radius over here, and theta is this angle. If you see over here, all angles must be in radians. Let's say we are given theta as 90 degrees, we have to convert it into radians. The conversion, if you're not familiar, is 180 degrees equals to pi radians. So 90 degrees would just be pi over 2 radians. So for example, if you want to find the minor arc length AB, when theta equals to 90 degrees and r equals to 4, the arc length would just be 4 times pi over 2, which is 2 pi. That's your arc length. If you notice, there's a little sign major over here, and I've been using the term minor arc length because they can also ask you for the major arc length. This over here is the major arc length. And what theta will you be using? You will not be using this theta for the major arc length. You'll be using this theta. So similar to earlier, let's say we want to find the major arc length. We need to do r times theta, which in this case, the major arc length will be 4 times theta, which is 3 pi over 2, which is the radians conversion for 270 degrees. Let's say I want to find the area of the sector. What is a sector? This over here, this orange area, is the sector, or more specifically, the minor sector. So the area of this sector will be half r squared theta. Again, r is the same r, and theta is the same angle theta in radians. Again, let's say I want to find the area of the major sector, that will be this pink area over here. And the theta we'll be using is this theta over here. Now, before we find what the area of the segment is, let's move on a little bit to the area of a triangle. Now, if you're not acquainted with this formula yet, you may be thinking, isn't area of triangle just half times base times height? But not all the time are you given the height. For example, in this triangle, we are given two lengths and an angle. So how do we find the area of the triangle? This is just simply half AB sine theta, where A and B are the two lengths and theta is an angle here. These formula over here are separate from the formula below this. Over here, we don't have to use theta in radians. We can use it as radians and degrees, and we'll still get the same answer. There's one really important thing to note. The lengths A and B have to be subtending the angle theta. What does that mean? It means they have to be touching this angle theta over here. We cannot just be using this length over here. Using this length over here is wrong. So remember again, the two lengths A and B used in this formula have to be touching theta over here. Some people do like to call this angle C, so it becomes half AB sine C, and you'll see a bit why later. But first, on to the area of the segment. Again, the area of the segment is tied to all these formula, but it's not in the formula booklet. This is actually derived from the area of the sector and area of the triangle. Let's see how. The area of the segment, or the minor segment, is just this yellow area over here. Can you see the yellow area over here? That is the area of the minor segment. If you look very closely, the area of the minor segment just looks like the area of the orange area, the area of the minor sector, minus this triangle area. Am I right? And since we know the area of the triangle to be half AB sine theta, this area of the triangle is just half r times r sine theta. So in sum, this area of the segment would just be half r squared theta, which is the area of this sector, minus the area of the triangle, half r squared sine theta, which is this area, to get this yellow area, which is the area of the segment. And that's where we get this formula from. Again, since this is derived from the area of the sector formula, this angle must be in radians. Okay, enough about circles. We're doing trigonometry, so we should be focusing more on triangles, right? So let's look at right-angled triangles. I'm sure you guys know Pythagoras' theorem, a squared plus b squared equals to c squared. But in case you're not familiar, a and b are the two sides here and here, while c just represents the length of the hypotenuse, or the longest length of a right-angled triangle. Again, this only works for right-angled triangles. We'll be looking at non-right-angled triangles later. So Pythagoras' theorem relates three sides of a right-angled triangle together. The next part, which is related to the angles, we call this trigonometric ratios, or what I like to call tuakaso. In case you have a problem remembering, this acronym tuakaso actually kind of helps you remember all the trigo ratios. If you're not familiar with what the opposite, adjacent, and hypotenuse is, as I said earlier, the hypotenuse is the longest side of the triangle. The opposite will be the length opposite this angle theta over here. If you're trying to find the angle theta over here, the opposite will be here. However, if let's say my angle theta is over here, my opposite length will be over here instead. Just take note. Actually, if you found the opposite and hypotenuse already, the adjacent will be very simple to find. It's just the last one. So over here, since this is the opposite and this is the hypotenuse, this one over here is the adjacent. Again, if your theta is here instead of here, your opposite will be here and your adjacent will be here. Again, your hypotenuse is still the same because it's the longest side of a right angle triangle. How do we use the acronyms to help us? Tua means tangent theta will be opposite over adjacent. TOA. Ka, which will be cosine theta equals to adjacent over hypotenuse, or CAH. And finally, so, which is sine theta equals to opposite over hypotenuse. So SO and H. Okay, let's try out something. Let's say we have the opposite as 2 and the hypotenuse as 3. And we want to find out what theta is. We have the opposite and hypotenuse, so what we want to use is sine theta. So now we know that sine theta equals to the opposite over hypotenuse, which is 2 over 3. A reminder, how do you find theta? Theta is just sine inverse of 2 over 3. When you want to move the sine to the other side, it will become a sine inverse. Now let's say maybe I don't have the hypotenuse, maybe I have the adjacent instead. So let's say you have the opposite and adjacent. Which one will you use? We'll use tangent theta, because over here we have opposite and adjacent. In this case, we know that tangent theta will be equals to opposite over adjacent, which is 2 over 1. So theta will be equals to tangent inverse of 2. Now moving on from right-angled triangles, we have non-right-angled triangles. You can see here the formula gets a little bit more complicated, but these two formula are in the formula booklet, so don't worry about memorizing them too much. Before we start, let's define what the A, B, and C is, and the capital A, B, and C. Over here, we have A, B, and C as your three side lengths. Similar to here, we have A and B. The angles represented by the letters will just be the opposite side. So the big C will be the opposite side of the side length C. The big A will be the opposite angle from the side length A. And finally, this B angle over here is also opposite from the side length B. In case you're wondering, this would mean the side length C, and this would mean the angle C. So that's why some people call this half AB sine C, where C is just this angle that's opposite from the last length. Now I think the formula should be kind of self-explanatory. First of all, we have C squared equals to A squared plus B squared minus 2AB cosine C. So if you look here, we have three different sides, A, B, and C involved, and one angle, the big C. Again, please be cognizant of what things you're substituting into the formula. So the C over here will be the C, the angle C over here. They must be opposite to each other. Next, for the sine rule, this says that A over sine A will be equals to B over sine of B, which will be equals to C over sine of C. Now while this cosine rule relates three sides and one angle, this one relates two sides and two angles. Let's try out this question. Given the triangle ABC as shown in the diagram below, find acute angle BAC. So over here, we have two sides and we have one angle. And we want to find out what this angle is. So over here, we have two sides that are given and one angle. And we want to find a remaining angle. So since this relates two sides and two angles, we probably want to use sine rule, not cosine rule. In case you forgot, I'm going to write the sine rule down. A over sine A equals to B over sine B. Alright, the and A over here, remember that these two are opposite from each other, and the B and B over here have to be opposite from each other. If you look over here, we have the length B, which is the length opposite the angle B, so this is 3, and sine B, which will be sine 30 degrees, because we have the angle B. And then you have C over sine C. You have the length C as 4, but we'll be finding this angle. No worries, later we can just take 180 degrees minus 30 degrees minus the angle C to find our angle BAC over here. Let's do this. We have 4 over sine C will be equals to B over sine 30. Now if you watch the special angles video, which should be about 1 or 2 videos later, you'll know that sine 30 degrees is actually equals to half. So this right hand side will just be equals to 6. So we have this equals to 6, and this is 4 over sine C, which means that sine C will be equals to 2 over 3. Now if we put this into our calculator, we get C equals to sine inverse of 2/3, which is 41.8 degrees. There's actually one more answer, where we get 180 degrees minus 41.8 degrees. In case you're confused by this, I encourage you to look at the solving trig equations video. This will be one of the later videos in algebraic trigonometry. So anyway, we have C equals to 41.8 degrees or 138.2 degrees. Which one is correct? We want to find an acute angle BAC. And if we sum up B and C, right, this has to be less than 90 degrees. So if we try to find the angle A, we will see that this is 180 degrees minus 30 degrees minus 41.8 degrees, or 180 degrees minus 30 degrees minus 138.2 degrees, or 180 degrees minus 30 degrees minus 138.2 degrees. And this will get us an angle that is more than 90 degrees. So we probably want to reject that. So if we use this other angle of C, 138.2 degrees, what we should get is BAC, or angle A, would just be 11.8 degrees. So that's your acute angle BAC. Having two answers over here is what we call the ambiguous case. This is just a thing that happens sometimes for sine rule, so you have to make sure if the angle you're finding is acute or not. Thank you so much for watching. Here's the summary sheet for geometric trigonometry.